Hi
Hi,
everyone.
everyone.
I hope
I
I'm
hope I'm
audible and my
audible and my
screen is
screen is
visible.
visible.
Okay, so
Okay,
let's
so
get
let's get
started
started
now.
now.
So we'll
So we'll
first
first
revise
revise
whatever was
whatever was
covered in the
covered in the
lectures.
lectures.
1 minute,
1 minute,
I'm hearing
I'm
some
hearing
echo.
some echo.
Yeah, I think now it should be fine. So, yeah, in this week's live session, first we'll do a brief discussion of what was covered in the lecture. So, this week we covered regression, clustering, and classification. So, a brief overview of what is the meaning of statistical learning. So, there are three types. The first is unsupervised learning, where data is not labeled. So, for example, clustering is an example of unsupervised learning. So, labeling the data means, like in the input itself, we have to tell the computer what class it belongs to, and from there it will learn. So, that is the idea in supervised learning, where the data points have labels, and from the based on the input data points that we give, even when we give a new data point, the model will try to predict and classify it. And so finally, we have the semi-supervised learning, which is a mix of supervised learning and unsupervised learning. And the important concepts covered this week are, we covered more on regression. Like in week 5, we covered linear regression. So in this week, we start with nonlinear regression, and then we go on to logistic regression and other types. So, for example, in linear regression, it can be used when there is a linear relationship between the variables, but not always two variables will have a linear relationship. So if the relationship is not linear, so maybe it is quadratic or something else, maybe it's polynomial. In that case, we have to use a nonlinear regression. So one example of nonlinear regression, one of the types is polynomial regression, where so earlier we just had a plus b1x, like we just had x power 1 terms, but in polynomial regression we will have higher order terms like x square, x cube, and so on. So this kind of this is called as polynomial regression. So in the previous case, we fitted the model to find out what is B1 and what is A. Similarly, here also the concept is similar. Based on the input X and Y values, we will write equations and fit it to get these parameters A, B1, B2, and so on. And once we get the parameters, we can also do a statistical test to see how well the parameters have been fitted with the model. And so instead of doing this kind of an approach, there are also other approaches where, in some cases, you will be able to convert the equation from a nonlinear form to a linear form. So, for example, if you have an equation, like if you have an equation y equals px by q plus x, then you can convert it from this form. So here you don't see any linear relationship. It's yeah. So then if you take the reciprocal, so this, and then you can cancel the x terms. So it becomes 1 by y is equal to q by px plus 1 by p. And this you can write as, so this y, 1 by y, you can take as a new variable, capital Y. And this 1 by x, you can take as a new variable, capital X. So when you substitute it, you get a new equation, y equal to bx plus a. So for this, you can do the linear regression that we covered in the previous class. So from this nonlinear form, we have made it into a linear form. And the second method is nonlinear least squares method. So in the previous lecture, we discussed about least squares method. So basically, it means that if you have a set of points and you have to, like in the previous section, we discussed about linear. So if you have to fit this line, then the line will try to minimize this distance from the predicted value to the actual value. So this we did for a nonlinear previously, but the same concept, it can also be, sorry, previously we did for linear, but we can apply the same concept for a nonlinear function as well. So in this case, instead of it, drawing a straight line and performing least squares algorithm that we discussed previously from a straight line, this will be better fitted with the curve like this rather than going for a straight line. And here similarly we do the same thing of finding the minimizing the squares. And so the next important concept that was discussed was clustering. So clustering means if you have a set of objects, you have to make them into different groups. So, for example, maybe you're having a stationery box in which there are like everything, pen, pencil, eraser, everything is mixed together, and then you separate out the pen separately, you separate out the pencil separately. So, that is an example of clustering. So, this can also be done for data points X and Y based on how similar they are. So, for example, if you have a graph of X versus Y, and then there are some of the data points are low in X and low in Y. And then you have another group which are high in X and high in Y. So these you can divide them into two clusters. So these data points would be one cluster and maybe they are coming from similar inputs. And these would be the second cluster. So maybe in your sample you are having two different cell types. Then you may get these kind of two different clusters. So this is the idea behind clustering. And so there are different types of clustering. The first is agglomerative, meaning that you have individual points. So so first you get an individual point and then this you have to decide whether it's going to cluster 1 or cluster 2. Similarly, next the second point you have to decide. So from individual points you are merging them into clusters. And you also have divisive where you have one large cluster. So from there you will split them into different clusters. And one more categorization of clustering is flat clustering and hierarchical clustering. In flat clustering, there is no hierarchy, but in hierarchical clustering, it is a tree-like structure. So, a good example of hierarchical clustering would be the um, evolutionary relationships that we draw. So, this is about clustering. And how do you perform the clustering? So you perform the clustering by using distance measures. So for example, if you go back to the plot here, if you find the distances of all of these points among each other, the distance will be less because they are all close to each other. But the distance between these two points from the two different clusters, the distance would be more. So to perform clustering, you need a distance measure. So there are different types of distance measures that you can use. So the first is the Euclidean distance. So this is the normal distance that we use generally, this square root of x2 minus x1 the whole square plus y2 minus or x1, yeah, x minus y the whole square plus y minus. So this is the uh, Euclidean distance. And the second one is the Manhattan distance. So Manhattan distance is also a measure of how nearby or far away the points are. Sorry, this will be x1 minus y1. So here x comma y are the points. So in Manhattan distance, so there is no business of doing a square and taking a square root. So you will just subtract the two values and consider their mean value. So that is Manhattan distance. And the third one is the Minkowski distance. So Minkowski distance is a generalized measure. So generalized meaning, so if you compare Euclidean and Manhattan, in Euclidean we are doing a square and then we are doing a square root. So similarly, you can also do a cube and the cube root, or you can take the fourth power and take the fourth root, and so on. So in the Minkowski distance, so that will depend on this value p. So if this p value is 2, then you will take the square root, and here you will take the square, and then you will take the square root. So if the p value is 2, then it would be the same as the Euclidean distance. But if the p-value is 3, then instead of square here, you will take a cube. And instead of square root, you will be taking a cube root. And finally, we have another distance called the Marlen-Boyce distance. So this is a special kind of distance, which it not just considers where the points are located, but it also considers the correlation between them. So this S that you see here, that is related to the correlation here. So if the two variables are correlated, then this value will be different. Whereas when the two variables are not correlated, then the value would be different. And there are also other distances like chord distance and correlation distance and Hamming distance. So this chord distance is like you have to consider the angle alpha by, so this alpha you can find by cos alpha first, by just you just have to substitute the values of x and y, and then this alpha cos alpha that you find, you can substitute it into root 2 into 1 minus cos alpha. So something, this would be the, so maybe there are these 3 points, and this would be alpha. And then you have the correlation distance. So in the last lecture itself, we discussed what is uh, covariance. So covariance means how much similarity is between the data sets. So if both x and y, it will say whether when x is increasing, it will say whether y will also increase or whether y will decrease. So from the covariance, we can find the correlation by dividing it by the uh, sigma x into sigma y. That is the variance of x and y separately. So this is just to normalize the covariance. But this correlation, if you recall from the previous lecture, I think someone's mic is on. Please mute it. Okay, so let's continue. Yeah, so I was talking about correlation. That correlation, can someone tell me what is the range of correlation? What is the minimum value it can take and what is the maximum value it can take? So correlation, it is not from 0 to 1, it is from minus 1 to 1. Because the two variables can be anti-correlated as well. So minus 1 means when x is increasing, y is decreasing. And 0 means there is no correlation. So the points are like everywhere. So this would be the 0 case. And 1 means when x is increasing, y is also increasing. So this is the problem with correlation, that it is going from -1 to 1. But for distance, it would be better to have a metric which is from 0 to 1, so that it will be easier to compare. That is why once we find the correlation, we substitute it into this formula. So then it will come to be in the range of 0 to 1. And yeah, so these are the different uh, types of clustering to group the data into these two groups. So once we have made these different groups or different clusters, based on this, we can start to classify them. So in classification, what we do is, given the data, we will put them into different classes. For example, maybe we are diagnosing, we have some test samples, and those samples we have to classify as cancer or non-cancer. So that is the first step, will be to define which is the categories that we are interested in, or what is the basic use that we want. And the second step would be to do some training of the model. So maybe in this case, we can give X-ray images, and initially we have to label the image as well. Labeling meaning, like, we have to explicitly tell the computer that this X-ray image corresponds to a cancer sample, this X-ray or cancer patient, but this second X-ray image is corresponding to a non-cancer patient. So when we give this input data, then the next step is to do a machine learning model. So it will learn from the labeled data to distinguish between cancer and non-cancer. And finally, so once we have this machine learning model, we can use the model for classification. And so now we can try to understand how this machine learning model works, or what is the basic principle that is like the that is used in a machine learning model. So one important um, component of the machine learning model is called logistic regression. So logistic regression, the main thing you have to remember, that it is the curve will be in the shape of an S. So this is called a sigmoid curve. Sigmoid, SIGMOID, sigmoid curve. And this y-axis is actually a probability. So since it is a probability function, it will range from 0 to 1. And yeah, this curve is a sigmoid curve, which lies from, its minimum value is 0, and then there is a increasing part, and after the increase, like here there is an increase, and after that the rate of increase decreases. So this curve will basically follow this equation. So in a logistic regression, we have to find out these two, A and B. So this is the equation that is corresponding to the logistic regression curve. Yeah. So, and finally, once you have the model ready, and the model is also classifying your data, so maybe you are giving some input images, and the model has to classify whether it is a cat or a non-cat. Then you have to measure how much the performance of your model. So for to do this, there are two important terms. One is sensitivity, that is the true positive rate. So for example, if if you give maybe some 100 images, And out of the 100 images, your model is saying that 50 of them are cat images. But in reality, only 40 of them are cat images. So even it has made a mistake of considering some non-cat images as cat images. But say there is another model, there is a different model. So this model also, it is out of the 100 images totally, uh, actually the number of cat images are 40. But this model is saying, this second model is saying that the number of cat images are 45. Then the second model is doing better. So this sensitivity is a measure of how much is the true positive. And the second measure is the specificity. So this is a measure of how many cases are truly negative. So like just like specificity was for true positive, that is out of the 50 cat images the model predicted, only 40 are the actual cats. So 40 is the true positive rate in this case. And similarly, the second is specificity, where true negative means, so maybe the model is saying that 60 of them, sorry, 50 of them are non-cats, but in reality, 60 of them are non-cats. So that would be the true negative value. So that is measured with specificity. So these were the important concepts discussed in the lecture. So now let's go to the problem solving sessions. So you can take a couple of minutes to go through each question, and you can type the answer in chat box. Then we will discuss the solution. We also have some quotes to discuss today, so it will be better if we go a bit fast. Actually, there is a slight confusion in the slides. So this, just a minute, let me fix it. This option A is actually the question. So this is the question. So this last one will be option D. Option C. Yeah. So y is equal to 1 by x plus 2. This is option C. Y equal to 1 minus 1 by 1 plus 2x is option B. And 1 by y is equal to x plus 2 by x. That is option A. So sorry about the confusion. There was some slight problem with the slides. Okay, you're not able to see the slides. Sorry, I'll share the window again. I was editing the PowerPoint, maybe. Yeah. So I've just changed the option A, option B, option C, and option D now. Just the order of the options has changed. Otherwise, the question is the same. So I can give a hint. The first step will be to take a reciprocal of this. So you have to take a reciprocal of it. When you take reciprocal, this x will come to the denominator, and this 1 plus 2x will be in the numerator. So you have to divide 1 plus 2x by x term by term. So that is the basic idea. Now you can try to solve it. Yeah, so you have got the answer correct. The correct answer is option D. So just a minute. Actually, here also this is the question. So this last one is option D. So this is the question, y equal to x by 1 plus 2x. So when you take a reciprocal, it will become 1 by y is equal to 1 plus 2x whole divided by x. So in the next step, you can write the terms of the right hand side separately. So this 1 plus 2x whole divided by x, we can write as 1 by x plus 2x by x. So this will become 1 by y equal to 1 by x. So this x and x will be cancelled, right? So this will be cancelled. And 2 will be remaining. So the correct answer is 1 by y equal to 1 by x plus 2, which is option D. So let's go to the second question now. Anyone has the answer for the second question? So when you type the answer, type it with the question number. So they have given two model. The first one is a plus y equal to a plus bx, and the second model is y is equal to a plus bx plus cx square. So basically, it is having an extra x square term, and the x square term is multiplied this constant c. So, and we have to compare both the models. So if you notice here, if you set c equal to 0, then model 1 and model 2 will be the same. So when we are comparing two models, two different models, so that will be our starting null hypothesis that model 1 and model 2 are same, or there is no difference between them. So the correct answer is option A, c equal to 0. So suppose you are interested to find out, uh, maybe your actual hypothesis would be model 1 is better than model 2, but your null hypothesis, as we discussed in the previous lecture, null hypothesis would be the opposite of it, which is that both the models are the same. So you have to set c equal to 0 for that. So let's go to the third question now. So this is a very simple, straightforward question. We just discussed the sigmoid function. So if you want a hint, I can go to that slide. Yeah, the correct answer is 0. So as we saw here, the sigmoid function is actually this y-axis is the probability, which ranges from 0 to 1. So the minimum value is 0 and the maximum value is 1. So the answer to the third question, minimum value of the sigmoid function is 0. So this question is based on specificity. So if you want, I can show you this. Specificity means how many negative cases are actually truly negative. So that is the definition of specificity. And in this table, um, so here you have the actual. So actually 0 comma 0 is like class 0, the predicted class 0 and actual class 0 are 50. So this is the confusion matrix. Based on this, you have to get the final answer. So this will, I think, take some time. So you can take about 3 minutes for this, then we can discuss the solution. So this 50 means that it is actually class 0 and it is also predicted as class 0. But this number 8 means that it is actually class 1, but the model has predicted it as class 0. So you have to interpret it like that. So to get the specificity, so first we have to find the number of true negatives based on this table. So true negative means the values that are negative, or the values, sorry, um, the actual negative or the actually false values that the model has also classified correctly. So it would be, it should be zero, and the model has also predicted it as zero. Yeah. So this would be the true negative. And in the denominator, we have number of true negatives, which we found it is 50. So it is actually zero, and the model has also predicted it correctly as zero. So that would be 50 divided by false positives. So false positive means that the model has predicted it to be positive. That is, the model should predict it as 1, but actually the value is 0. So that would be 30. So this 50 is the true negative, and this 30 is the false positive. So now we just have to apply it into the formula. So in the denominator, we have true negative, which is 50 divided by 50 plus 30. So this would be 50 divided by 80, or 5 by 8. So this would be about 0. Sorry, 6, and then 20 will be remaining. So 2 pi. So the correct answer is 0.625. So let's go to the next question. I hope this is clear to all, this question on specificity. Any doubts? Because this is an important concept. If you have any doubts, we can discuss it. Otherwise, we can go to the next question. If you have any doubts, just raise your hands. I'll wait for a minute. Okay, I don't see any hands up, so I hope it's clear to all. We'll move on to the fifth question. And this you can take a couple of minutes to answer, then we will discuss it. So this question is based on the Akaike information criterion. So it is a measure of how good a model is. So basically, it considers two parameters. So one is how many parameters are used in the model, and how well is the fitting of the model. So if the number of parameters are more, then the value will also be more. And if the um, fitting is better, then the value will be lesser. So the lower it is, the lower this AIC value, the better is the model. So lower AIC value means that for even with less number of parameters, the model is doing a good fit. So based on this, now you can try to answer the question. Yeah, the correct answer is A. The model with AIC equals 98 because it is the lowest value. So the formula for AIC is 2k minus 2 ln n minus 2 ln. So here k is the number of parameters in the model. So if there are more number of models, then the AIC value will be more. So it is penalizing the models which have many parameters. So if you just consider sum of the squares as the metric, then maybe so what people do is they try to put more and more parameters to make the model to fit well, but it will make the model more complicated and it may also lead to overfitting. So we also need a measure where the number of parameters should also be minimal. So that's why we have this measure of AIC, which accounts for both number of parameters in the model and how well the model fits the data. Let's go to the sixth question. So here they have given um, four genes and their expression values in three different samples. And they are asking to find the Euclidean distance between gene 2 and gene 3. So the formula for Euclidean distances. So first we or the method to find out is first we have to subtract them and take a square root. And these squared values we have to add up. And once we have done the addition, sorry, not as first we have to subtract, then we have to square the difference. Then after squaring, we have to add everything together. Then we have to take a square root. So here they are asking Euclidean distance between gene 2 and gene 3. So the first step is subtraction. So 1 minus 1 is 0. And 2 minus 2. So these values we are considering 1 minus 1. And the second row is 2 minus 2 is also 0. And the third row is 3 minus 2 is 1. And now we have to square these differences. So if you square it, first term would be 0 square, which is 0. And the second would also be 0 square, which is also 0. And the third would be 3 minus 2 the whole square, 1. And now all these three, if we add together, 0 plus 0 plus 0 is 1. And finally, we have to take a square root, which will also be 1. So we have just used the formula square root of x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. So for the sixth question, the correct answer is option 1. If you have any doubts, you can raise your hand. Otherwise, we can move to the seventh question. Okay, I hope it's clear to all then. Let's go to the seventh question. So seventh one is actually a straightforward question. So here they are saying that first they have already created the model using nonlinear regression. So we already have the model, so we don't have to worry about getting the model. Now with this model, they are interested to get the outcome for new inputs. So which function will we use? The correct answer is option A. Predict is the function. So using the model, we are now using it to predict it for other new inputs. So you can remember it easily like this. And we can also look at the other options. Option 2 is NLSLM. So this NLSLM stands for nonlinear least squares with a linear model. Nonlinear least squares with a linear model. So this is used for model fitting. But here they are saying that they have the model already and they just want to predict it. So that's why we are using the predict function. And the next option, QLM, this stands for quantilinear model. So this is also another type of model used for estimating the quantiles. Quantile, sorry, I messed up linear. And summary, I hope all of you know, we have used it many times in the previous week's coding sessions. So it is used for giving the some of the statistical measures of a column. Like maybe it will give the mean, median, variance, and so on. So that is the summary function. So it will give the column. Okay, so let's go to the last question for today. After this, we will be going through the codes that was discussed in the classes. So here they have given what is the equation that we want to fit. So we want to fit BMI and as a function of age. And we are going with the cubic equation. BMI is equal to A plus age squared plus A cube. And they are asking uh, which of the following R code is suitable for this regression. So here so in the previous class we were doing linear regression and there we used the LM function. So here also we can use the same LM function. And but here it is not linear. So here you have to write the y. So in this case, y is nothing but this BMI, which is on the left hand side. BMI and separated by this tilde. And we are fitting a polynomial. So we are writing this poly here. And this poly is for this age variable. So we are writing age. So the first input to poly would be which variable we are using. And this 3 is nothing but what is the highest degree, which is for a cubic equation, we are going up to age cube. So this is 3. And draw equal to true, meaning it will take the raw data. And we have to specify from which of the data frames the model has to take the data from. So that is in this BMI underscore age underscore data set. So that's it for today's MCQs. Now we can discuss the codes. So I hope all of you have the codes for lecture 6. I'll give you a couple of minutes to open RStudio and to open the codes for week 2. So week 2 code A. This is I'm also opening it. So this code is for performing polynomial regression. So if anybody doesn't have the code, you can raise your hand. You have to download it from the Swayam portal. If you're not able to get it for some reason, I can also copy paste it in the chat box. Just please let me know. So let me stop sharing my presentation and I'll share my RStudio. So meanwhile, all of you also please open RStudio and the code for week 6, lecture 2. And it would be good if you can also run the code at the same time so that if you have any doubts, we can discuss it in the live session itself. So I hope my RStudio screen is visible now. And I hope all of you have also opened RStudio and you have opened this 2_week_6a.r script. So I'll just wait for a minute. If anybody has not opened, please raise your hand. Okay, I hope everybody has it open. So this first code, we are trying to fit a regression model. Which is of the form b1x plus b2x square plus b3x cube. So in the previous lecture, we only did up to this part, a plus b1x. We didn't have any higher order terms. But now we are trying to fit it for higher order terms as well. And we are doing it for the data set of temperature versus yield. So we are trying to predict as the temperature changes, how will the yield change? So first let's read the data. So this data is available. So this data is loading here. So the data has loaded. So now first we have to check what is in the data. So to do that, we are plotting temperature and yield. And if you want, we can also check um, what are the columns in this data set. So I'm just typing YD. And you can see that there are two columns, temperature and yield. So this is the temperature column and this is the yield column. So this temperature is written first, meaning that it will be the x-axis, and the column that is written as second will be the y-axis. So now we have plotted it. If you can see the plot here, and we have given red color, so the points are coming in red color. So now this data we have to try to fit. So just by looking at it, you can see that it seems to be like a quadratic equation. Like you can see that it is decreasing till here and then increasing. So like a quadratic equation. But anyways, that is the first thing. We will try to fit a quadratic model. So this yield, that is the dependent variable. So that will be in the y-axis is equal to a plus b1 into temperature plus b2 into temperature squares. So here to fit a quadratic equation, we can use the same LM function that we used previously. So the format is similar. The syntax is similar. It's slightly different. So the first term, this is the same, that we have to fit yield or the dependent variable. That will be the first term, tilde. But here extra, we are having this squared term. So to use the squared term or these any of the higher order terms, we have to use the I function. So we are mentioning that it is for temperature for this term as well as temperature square for the higher order term, right? And so the function is the same LM. So just this term is extra because we are having an extra term in our equation here. And as usual, we have to specify which data the model has to fit. So that is this YD data set that we have read here. So if we do this, it will fit it. And now if we do summary, we will get the different parameters that we have got. So this intercept would be your A, and the coefficient of temperature would be B1, and this coefficient of temperature squared, that would be B2 in the equation. So this is one method of using the LM function, and you can specify the higher order terms using I. And so this is one of the syntax. The other syntax is of this form, same LM function, and this is not changed because again we are trying to predict yield. So yield will be the first input, followed by a tilde. And here we are using the uh, poly function. So in poly, we have to write which is so the first input to poly would be the x-axis, or which is the independent variable. And the second input would be what is the highest order term, which is squared here. So it is 2. We are considering it as the same input data set. So raw equal to true. And as usual, data equal to YD. So this is what we discussed in our uh, MCQ session as well. So the same thing you can do in two different ways. One is you can specify each of the terms, including the higher order terms using I. And the second method is you can use the poly function and just write what is the highest order term, which we are fitting a quadratic equation. So it is 2. So summary, right? So if you check the estimates of the intercept with the second line of code is 7.96 something, and here also it is 7.96, and the temperature coefficient is minus 0.1537, and here also it is minus 0.1537. So we are just doing the same thing in writing the code for the same thing in two different ways. So that's why they are the same. So now we have got the model. Now the next step would be we can try to create a vector and predict it. So this XV is the input vectors, or the X vector that we are trying to predict. So in the model, like, these are the points. So based on this, now we want to predict that suppose the temperature is 50, then what will be the yield? Or suppose the temperature is 100, what will be the yield? So this is the known information. Based on this known information, we are trying to predict something using the model. So to do that, we have used the predict function that we have already covered in the MCQ session as well. And now we are also fitting the curve. So this blue color is the fitted curve. So here we have done a regression model for a higher order term using including the higher order term using the same LM function. So that is the takeaway of this. And there are two methods to do it. One is using the I method, and the second one is using the poly. So let's go to the next code of week 2. So here we are going to see how to do nonlinear least square method with R using a plant data set. So we are first reading this plant data. And if you want, we can check what is in the plant data. So it is having one column is called week and one column is called mass. So at how many weeks? Like at 1 week, it is the input data is 4 and so on. So now we have to predict. Suppose somebody is telling you that the plant is 5 weeks old, you have to predict what would be its mass. So now first let's plot the data and see to make a guess about which of the distribution would fit it. So you see this kind of a trend. It looks like a exponential to me, but let's see what we can use. So we have to perform a nonlinear least square fit. So to do a nonlinear least square fit, this also we mentioned in the MCQ, we have to use the NLSLM function. So this NLSLM function is a uh, function from this package called minipack. So first I will try to load the package, but I'm not sure if I have the package or not. So let's see if I have the package or not. So I'm getting an error that this package is not there. So that is happening because I have not installed the package. So now we have to first install the package, and you can do it with the command here. So you can just use it in the command line. So what you have to write is install dot package, and then in brackets you have to write within quotes the name of the package, which is minipack.lm. So if any of the others, if any of you also, if you are stuck in this point and you are getting the same error, then sorry, I pasted it twice. Then just write this line install.package minipack.lm. So I will also put it in the chat box. Mm, wait. So you can also write the same line. 1 minute. So I have put it in the chat box now. Dot package. So I'm installing it here. Install dot package. I think I have not updated my RStudio. That's why I'm not able to install new package. Let me check. So what about the others? Are you able to? Oh, okay. Sorry. So I made a mistake. So it is not install.package. It is install.packages. So you have to add an S. That's why it is not coming. So now I have written the correct function and it has worked. So it has downloaded it. Now we can load the package using this library function. And once we have loaded the package, we can use the NLSLM function. And again, this NLSLM function has a certain syntax that you have to use. So this first input is the same. It is the dependent variable that we are trying to fit, that is mass. And this tilde sign, same that we had for LM as well. And then you have a to the power. So as we discussed that it looks like an exponential function if you see here. So there is an increase and then it is leveling off. So that's why we are trying to fit it. We are using this exponential function here. And we can also tell the function like what can be the starting values for this NLSLM. So we have to, so this starting value is just based on a guess. So we have guessed it as 25 and 9, but you can also give other numbers. And the data is the same plant data that we have loaded here. So this is the function that we are trying to fit is mass is a to the power 1 minus e to the power minus b into week. So this week is the dependent variable and we have two parameters in the model, this a and b. And this a we are guessing as 5 here because as you can see the starting value is around the value of 5. So when this term is initially 0, then it would be, and if you just consider this value should be 5 based on the plot that we have here. So now we have done the fitting. So let's try to see what are the values of A and B that we have got. So let's see. So the estimate for A is 26. So our starting guess was 25, but the estimate is 26. And the estimate for B is 0.17. So now we have created our own vector, like 1 week, 16 week, and 0.1 week. And for this, we can predict based on our model. So if you want, we can check what is there. And after the prediction, we can also plot it. So this is the final plot of the fitted function. So this was what was discussed in the lecture 2 of week 6. Let's also discuss the code from lecture 5 of week 6. So here we are doing a logistic regression for classification. So let's go over this code every step by step, every line by line. So it's quite big, but nothing to worry about. We can go over line by line so that there is no confusion. And the code also has comments. So if you want, based on the comments, you can also try to read and understand on your own. So that's what we will be doing now as well. So this is the data set that we have, which has cell nucleus features from some digital images of breast tumors. And so this original data has been trimmed by some analysis. So, so this data set, if you can see, it is from breast tumor. And so this tumor can be of two types, malignant or benign. So malignant is defined as 1 and benign is defined as 0. So this is finally what we want to predict. We want to predict based on the nucleus image whether the tumor is benign or malignant or benign. And so this, based on what we have to predict from this nucleus images. And here in this case, we have the nucleus radius and the nucleus area. So this is the problem that we have. So let's see how to do this. So we have to train the model such that there is an initial data set, and from this data set, we have to train it to also predict it for other samples. So let's first load the training data set. So I will copy as path and paste because it is not reading. So here we have two data sets in this week folder if you have downloaded it. So one is the test data set and the other is the training data set. So right now we are going to train the model first. So we are just reading the train data set. So the training data has been loaded and now this line is just plotting it. So the values are just two different values, like we have 0 and 1. So 1 means it is malignant and 0 means it is not malignant or it is benign. So this, as we discussed, we can try to fit this with the logistic regression sigmoid curve. So that's what we are going to do because it is a probability measure on the y-axis. So we have plotted it and now we are using a logistic regression. So this is the formula, which is 1 by 1 plus e to the power minus 1 of a plus bx. So this a and b are the parameters that we have to find. So if we take the log on both sides and rearrange it, so we will get it in a simpler form of a plus bx is equal to ln of p by 1 minus b. So here this p is the probability or what we have on the y-axis, and a and b is what we want to get. So to do that, we can use this GLM function, which is generalized linear model, because now we have written it of the form a plus bx. And this MAL, or whether it is malignant or not, so that is the variable that we are trying to predict, and we are predicting it with the area, so tilde area. And the data is the training data set that we have read already, and the family is binomial. So let's try to see what values of A and B we have got. So the intercept here is this A, which is about minus 5 point something. And the area, this X is area, so the coefficient of area is B. This B we are getting around 52.88. So it will be better if we try to also plot it. So here, as you can see, the input data set is from this training data set is from 0 to 0.3. But to plot it, we are making a vector which is going from 0 to 0.4. So this will be the X, and we have to find the fitted value as well. So to find the fitted values, we just have to substitute the values that we have got into this equation. So this is the line where we are substituting the variables a and b that we have got into the equation. So now we have got the fitted response or the predicted response. And now we have to plot the input sequence versus the predicted sequence based on the A and B that we got from the model. So as you can see, we have got a sigmoid curve because basically we have plotted it into a sigmoid function. And now we have to find a cutoff that if it is above this, then the probability is it is malignant. But if the cutoff is below this, then it is not malignant. Something. So we have to calculate the cutoff threshold. So this cutoff threshold that we can decide on our own. So in this case, we are considering p is equal to 0.5. So 0.5 is somewhere over here. So it corresponds to area between zero point 0.1 and 0.15. So we say that if the probability is greater than half, then it is malignant. If the probability is less than half, then it is not malignant. So this p-value is 0.5. So this 0.5 we can put here. And when you put p is equal to 0.5 here, we have to find what is x. So when p is equal to 0.5, this x would be the threshold area, right? So that will be minus a by b if you just simplify this. So if you want, we can try to simplify it as well. 0.5 is equal to 1 by. So I'm just copy pasting here, and instead of p, we have to substitute 0.5, the cutoff value. So now if you take, so if you simplify it, you will get minus a by b, and we have calculated it. And we are now just drawing a vertical line at this threshold. So if the nucleus is having an area less than this cutoff, which is around 0.110 something, then it is not malignant. So now we have got our model. The next step is to, sorry, do it for the test data set. So for doing that, we are using the predict function, and we have to predict it with this model that we have built, which is logit.area. So the input to the predict function, the syntax is first you have to write the logit.area. So now based on the, so this model will predict the value of y. So once you get the value of y, you have to classify it as benign or malignant. So for that, we are using this conditional statement that if this value predicted, this p1 is greater than 0.5, then it is 1. Otherwise, it is 0. So this C1 will be the final output, whether it is 1 or 0. So now these values that are predicted, we are comparing it with the actual values and we are printing it as a table. So this has given us the confusion matrix that we discussed earlier. And now we can try to measure how good the model is doing by finding its specificity and sensitivity. So specificity is true negative by true negative plus false positive. So the true negative is this first term and the false positive is the last term, like what we discussed in the question today. So we are substituting the values here. True negative 1 comma 1 term divided by false positive. Now let's see what value we are getting. Print. So it's coming about 0.95 and sensitivity is true positive by true positive plus false negative. So true positive would be the number of samples that are malignant, which which the model has also predicted to be malignant. So the predicted should be 1, actual should be 1. So true positive would be the 2 comma 2 term here. So second term, second column term. That is the true positive. So we have written in the numerator 2 comma 2. And the sensitivity is 0.8. So this is the first model. Here we have taken it with just one predictor, which is the area, but we can get from the input data set, it also has another variable which can be used as a predictor, which is the radius. So this is the second thing that we are going to do. We are going to build another model. Here we are using not just area, but we are using two predictors, which are area and RAD or radius. So here also we are following the same steps that we followed before. So we are first building the model with the GLM function, and then we are predicting the probabilities, and we are setting the same 0.5 cutoff here. So if this predicted value is greater than 0.5, then it is 1. So 1 means it is malignant. So that is what we are doing here. And just like before, we are making the confusion matrix to calculate the specificity and the sensitivity to find out how good is the model. So here the specificity is 0.925 and let's see what is the sensitivity is 0.8889. So here it is 0.95, but in the previous model it was 0.952381 and 0.952381. So now we have built the models. We have to try to test it with the test data set. So we have to first, so this is an example of labeled data set because in the data set, this training data is an example of labeled data set because it is having the information of whether it is malignant or not. But now we have a test data set which will not have the information of whether the sample is from malignant patient or benign patient, and it is the job of our model to predict it. So we have loaded the test data set and to predict the probabilities from this test data, we have to again use the predict function, and we are using it with the model that we made with the logit 2 with the GLM function. So once we have uh, so when we predict it, we will get this y-axis probability value. Then we have to set a cutoff, and we are making a confusion matrix again to check how well our trained model is performing on the test dataset. And again, we have to find the specificity and the sensitivity. So specificity is the true negative rate, which is about 0.952381, and sensitivity is the true positive rate. So that's it for today's class. So once again, these are the topics that we discussed today: regression, clustering, and classification. And we have also performed some exercises in R. So does anybody have any doubts? So in this, I hope you are clear with the specificity and sensitivity concept. If you have any doubts, you can go through my um, problem solving. So there was a problem, I think. Yeah, the fourth problem. So if you have any doubts, you can go through that again. And you can also try to run the codes on your own. So if there are no doubts, we can end the session for today. If anybody has any doubts, we can discuss it. So I hope it's whatever we discussed is clear to all. If you have any doubts, you can also post it on the discussion forum. Okay, so that's it for today's lecture then. We can meet again next week.